Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. We will continue our discussion of antennas. I would like to just motivate this module by bringing up one of the results from the last module, namely that of the radiation resistance. Now, recall that radiation resistance is how a circuit would look or how the circuit would view the antenna as such, right, because the antenna is radiating power and that power will be supplied by some source, and the amount of power that is radiated would something that the source would never get back, right. So, it is a power that is being lost, as far as the source of the that power is concerned. So, the voltage generator that you would have kept in order to feed the antenna, as far as that voltage generator is concerned, this power that is lost or radiated by the antenna is something that is lost from the perspective of the voltage generator, okay. And that is the reason why we represent that power radiated by an equivalent resistance and call that as radiation resistance, right. So, that resistance is how the voltage generator would look at an antenna. So, regardless of what antenna type that you consider, you can of course, with some approximations that we have been that we have not talked about, but there are a lot of approximations here, but you can with those approximations replace the antenna as far as the circuit is concerned and then represent that one by a equivalent radiation resistance. Now, one of the things that you would like when you are using an antenna for transmitting information from one point to another point by radiation would be to maximize this amount of power that is being radiated. So, suppose I send in 1 watts of power from the voltage generator or the power generator, feed it through the antenna, and if only like 1 milliwatt of the power is radiated, then most of the power is either lost or rather most of the power is not being sufficiently utilized in order to transmit information. Yes, that power would be remaining within the source, but that is not what we want. What we want is to maximize the radiation, that is because unless I maximize the radiation, then the receiving antenna cannot be kept at a very far distance. We will see the relationship between the transmit antenna power or rather power density and the receiving antenna and the distance between these two in order to get appreciable signal at the receiving antenna later on, but it is kind of obvious from physical intuition that if you only transfer a very small amount of power that is being fed to the antenna and make it radiation, then that is not a very good antenna, right. So, what you want is a situation where the antenna radiation resistance should be larger, right. So, one of the ways in which you can do this is what we are going to consider in this module, and we call this as a linear antenna. Sometimes it is also called as a thin wire antenna or sometimes called as a linear wire antenna, and the length of this antenna will not be very small. So, in the case of a short elementary dipole that we considered, the length of that dipole dz was considered to be very, very small compared with the wavelength. Now, we do not make that approximation, and we will see that if the length is made appreciably close to the wavelength of the wave that is being radiated by the antenna, then the radiation resistance can be improved significantly. Okay. So, with that in mind, let us look at what antenna that we are going to consider. This is one of the more practical antennas, okay, and this antenna is usually center fed, meaning that the voltage generator that you have with appropriate internal impedance would be connected via a transmission line to the antenna terminals, okay, and then connected connected to the antenna at the middle of this antenna terminals. Of course, I have shown this gap to be very large, but in general this gap would be very, very small. So, a proper representation would have been something like this with the transmission line connecting the antenna up here. Okay. The gap should be there, but the gap is considered to be very, very small. Okay. And we will put some length here. So, if you consider this as the z equal to 0 point, then this fellow at the top portion will be z equal to plus L, and this one would be z equal to minus L, and this is the antenna part, and this is the transmission line feed to the antenna, and this of course is the voltage generator that will be generating whatever the power that is necessary to feed to the antenna. Okay. Of course, information will be residing in this voltage and it would be time varying, so that the current that the antenna would have, the antenna current or the current on the antenna terminals will be dependent on what voltage and transmission line feed that we are using. Okay. And because of this current which is varying with respect to time, you will have this A field, that is vector potential, and by calculating the vector potential you can then calculate what would be the electric field and the magnetic fields of this antenna as radiated away, right. So, that is where we would like to go. So, in the elementary short dipole or the short dipole that we consider, the elementary dipole that we considered, we were particularly not worried about the current distribution on the antenna terminals, right, because we had this antenna itself to be very small compared to the wavelength. We took the current to be constant over the entire antenna terminal. So, you had this antenna which was fed, but then the current over which we had was considered to be constant. So, no matter at what point on the antenna that you took, the current was essentially the same. You could make this approximation because the length of the antenna was very small compared to wavelength. But now the situation is not like that. The situation is that you have your length, the total length of the antenna is 2L as per what we have considered here, is actually comparable to wavelength of the fields that it is radiating. So, because of that you cannot simply make the antenna current to be a constant. So, then that leaves us one big question: what is the current distribution? Okay. What is the current distribution on the antenna? Now, unfortunately for us, there is no specific answer, because this problem is so difficult that we have so far not been able to calculate or determine the exact current distribution on the antenna terminals. If you make this into an even more practical antenna, and instead of assuming them to be thin wires, you assume them to have some finite thickness, because any material that you construct will actually have, a copper wire will have some amount of finite thickness, and the copper will also not be a perfect conductor, there will be some losses in that one. And if you consider that more practical scenario, then finding the current distribution is almost impossible. In fact, it has not been possible for us to determine what the current distribution is. So, unlike the elementary dipole discussion where we straight away started with J and then we wrote down A and then we found out E and H, of course, with lot of tedious mathematics, that procedure unfortunately breaks down unless we make some approximations to the current distribution. In practice, what we do is we use lot of numerical techniques to obtain a better approximation, okay, of the current distribution on the antenna terminal. Why this current distribution is very difficult to determine, which is one of the central problems in antenna theory, is something that you will have to learn in a different course on antennas itself. But for now, you can kind of motivate yourself to see that this particular antenna that we have considered can be thought of as being starting off with a simple tapered transmission line and eventually flaring up over, right. So, you can think of this antenna as being starting off with a straight transmission line, and then as you start bending the two wires of the transmission line at different angles and eventually reach 90-degree bend, then that would be the antenna that you would obtain, which we have called as a linear antenna, right, a linear or a thin wire antenna. And we know that because there is an open circuit at the ends, right, the current distribution has to be in such a way that you will have. So, of course, it also depends on the length that you have. So, for example, if the flaring length happens to be say lambda by 4 here and lambda by 4, then this situation is actually originally corresponding to a transmission line whose length here is about lambda by 4, right, and that is what we have taken this length and then bend it in this particular fashion. So, on an open circuit and you connect this transmission line, what would be the current distribution? The current distribution would be something like, or the voltage distribution, let us say, the voltage distribution will be maximum at the open circuit, right. So, in the open circuit, yes, it would be maximum, and over lambda by 4 it would have reached a minimum, right. So, this would be the current voltage distribution. The current distribution of course would be minimum at the gap, but then it would reach the maximum. So, this could be the current distribution, right. So, this is the current distribution that you have considered. So, essentially if you think of now the two wires being bent and imagine that the length is about lambda by 4 and lambda by 4, then the current distribution could be well approximated in this particular manner. Okay. So, it could be now if instead of lambda by 4 you make it lambda by 2, then what happens? Then you should actually consider the fact that the current distribution would look something like this. Of course, is this the correct answer? Not really, but this is a very good approximation. So, as the length of the antenna increases, you will actually see minima, maxima, but this motivation which we have done it from the transmission line theory is only a motivation, okay, because it has been found that the current distribution is not exactly a cosinusoidal distribution, but in some cases may even take a triangular distribution, okay, and you can even in some very low approximation consider it to be a step or a pulse like approximation, okay, so or a square wave kind of an approximation. But for analytical purposes we either consider it to be a triangular wave or we consider it to be a cosinusoidal waveform, okay, and we will assume that is the scenario over here. We will of course not write this as lambda by 4, we will keep it slightly general and say that this is L and L, but then we assume that the current to be cosinusoidal. Okay. So, since we took this as the z axis, rather because this is the source coordinates, we need to actually put a prime onto these coordinates, which is correct. So, the distribution has to be maximum at the center and then it has to be minima at these 2 points. Okay. So, with that let us write down the expression for the current distribution. So, I of z prime, which is how the current would be on this particular antenna, that would be equal to some I 0, which is the maximum of the current, times sin k L minus z prime magnitude. Okay. So, I will tell you the reason why I am writing this as L minus z prime magnitude, and then I have sin of k L. Okay. So, at z prime equal to 0, which is at the feed point of the antenna, the current would actually be equal to I naught, and at z prime is equal to 0, you have sin k L by sin k L. Yeah, the current will be I 0 and then it will go to 0 at the edges. Okay. Of course, k is in this particular case 2 pi by lambda, and the actual result will depend on L and lambda ratio as well. Okay. So, for one of the, so I should have probably considered this to be a lambda by 2 antenna. So, that is why I have put this cosinusoidal distribution or a sinusoidal distribution, but this is the distribution that we are going to assume. Okay. So, at z prime is equal to 0, you have an antenna current of I 0, which then goes to 0 at the 2 edges. But please understand that this is only an approximation, this is not the true current distribution, and true current distribution is a very complicated topic and there are no solutions for the true current distribution or the exact current distribution. Okay. With this current distribution, that is a well approximated current distribution that we have assumed, we can now proceed to the next steps. Now, I will minimize the mathematics here, I will leave most of it as an exercise for you to figure it out, but I will give you the expression for the electric field and tell you couple of approximations that we are going to make, because those approximations are necessary to obtain tractable analytical expressions. Otherwise, the mathematics becomes very tedious and will be very difficult for us to look at that one. Okay. I mean look at that in this short course. Okay. I know the current distribution to be given as z prime. The procedure next will be the same. The A field, the vector potential will actually be around, will be something like z prime A z, that is to say it has only the z component. Okay. And we know the expression for A z, right. A z is given by mu naught by 4 pi integrated the current distribution. So, you had this j dot ds or j ds, but now this is a linear antenna. So, there is no area here. So, it becomes instead of j times dv prime, sorry, that is the volume, now it simply becomes current times dz prime. Okay. And divided by r minus r prime, these are of course the observation and the source point, and you have a phase factor that would also multiply. This is the retarded potential part that you are looking at, and this is what you have the expression for. Now, we know that this is the antenna that we are considering, this is the feed line of the antenna. So, the source coordinate is moving along z prime, but then the observation point that I have, which if I take this as the origin of the coordinates, this would be the distance from the observation, from the origin to the observation point, which we will call as point P, and at any point on the source the current is of course I z prime d z prime at this junction. So, which is at a length of d z prime. This would be the radial distance r. R is the distance between the observation point and the source point, right. So, this is the observation point, source point, and of course, we are working still with the spherical coordinates. Okay. Now, because I have defined this capital R as this magnitude, that is this particular line, okay, this is the line that I am considering, I can simplify the expressions over here. Okay. So, first I will substitute the expression for I of z prime, which is the current distribution that we have assumed, and that would be I 0 by sin k L, and then you have sin of k L minus z prime. Okay. The magnitude of z prime, because z prime can go from minus L to plus L, covering the entire antenna region. Okay. And along with this one there is a denominator r, and then you have e power minus j k r. Okay. So, this integrated over the source element from z prime, which is from minus L to plus L. This, if you perform this, this is what you are going to get. Of course, you can also see that there is some amount of symmetry into this problem, in the sense that as you move around the antenna, if you leave out the gap part, if you move around the antenna, you will see that the current distribution would remain the same, right. So, if this is the antenna and you move, the current distribution would remain the same. So, there is a phi invariance in this particular problem. So, moving along the azimuthal will not really change the distribution, and that symmetry is built into this problem, because Az is now function only of capital R. Okay. Even then the problem is rather not simple to solve. So, we will have to make couple of approximations, and this approximation is something that you may have seen earlier in the dipole scenario, okay, but it is worthwhile to make that approximation. See, I am considering a particular point here at with a width of dz prime at a height of z prime, correct, and then I also am going to consider an similar point which is at a distance of minus z prime from the origin, but with a patch length of dz prime itself, that is the width is dz prime itself, and now I am looking at the observation point P here. Okay. Now, technically when I consider the point at z prime and dz prime width, the R value, the capital R that I am considering, let me call this as R plus, okay, and similarly I will call this fellow as R minus, okay, and whatever that is from the origin to the observation point, of course, is your distance R. Okay. So, I have 3 lengths, and you obviously know that R plus, or you can obviously see that R plus is kind of larger compared to the small r, and small r is smaller compared to, sorry, R plus is smaller compared to small r, and R is smaller to R minus, meaning that R plus is less than R, which is less than R minus. Okay. But imagine that my distance to the antenna is so large that this entire antenna would essentially appear to me as a single point. Then what happens is that these lines which kind of converge at point P can instead be considered to be 3 parallel lines. Okay. There are 3 parallel lines, of course, because one of them is at z prime dz prime, the other one is at z prime equal to 0, and the other one is at z minus z prime. The lengths of these will be slightly different, and if you move the point P, the distance as well as the orientation of these points move, right. So, if this is your antenna point, so let us say this is the R, and as you move the point P, the orientation will change. The orientation with respect to z axis, which we will call as angle theta, will change. Okay. So, calling this as angle theta, which is the angle between the observation point P, the length, the radial line between the origin and the observation point P, plus this z prime dz prime patch that we have considered, then if you approximate these 3 lines R plus, R minus and small r by 3 parallel lines, you get you can simplify the analysis, and what you get is something like this. So, let us first write down the small r case, and of course, this will work only when you have the point observation point P to be very far away from the antenna. So, that the antenna would essentially look like a point to you. Okay. Now, I am going to assume that this is parallel line, and I am going to assume that this is also parallel line. Now, what is the relationship between these three lines? See, if you look at r plus and small r, the only extra length that you have is this one, right. So, this is the extra length that you have. What is this extra length? I know that this is at a distance of z prime. I know that this length, I mean you do not really need to know that length, because you know what is this theta, and if you want to find out what is this extra length, right. So, what about cos theta? Cos theta will be this adjacent side, whatever the length that you want to find out. So, we will call that as say delta itself. Okay. So, delta divided by this would be the hypotenuse, right. So, that would be z prime. So, this will give you delta of z prime cos theta, okay, and therefore, you can write r plus as small r, which is this length radial line, minus z prime cos theta. And similarly, you can convince yourself that r minus, which is this fellow, can be written as r plus z prime cos theta. Okay. So, I can write in this particular manner. So, I am going to get this as r minus z prime cos theta and r plus z prime cos theta. Okay. Now, what is the use of this? See, the integral was actually going from minus L to plus L, correct. So, all these integrals were going from minus L to plus L. Now, I can break this integral from 0 to L and then one integral from minus L to 0. Okay. And in this integral, I will have only the distances r plus involved, and in the second integral I will have the distances r minus involved, but both essentially look kind of symmetric, and I can convert this integral from 0 minus L to 0 to L, and then rewrite the expressions for finding Az as, I mean I will split the integrals. Of course, I0 by sin kl is constant, so I can pull this out. So, I have sin kl here, and then this integral is from 0 to L dz prime. Notice here that I still have z dependence in the form of the current distribution. So, I do not have to now write magnitude z, because this is basically z prime positive only, right. And most importantly, in the denominator, this is the source point that we have, right, and the source point is basically r minus z prime cos theta e power minus j k r minus z prime cos theta. Okay. You may think that we have not really simplified the problem, because z prime is present in the denominator, z prime is present in the numerator. Luckily for us, if the overall length L is very small compared to the radial distance from the observation point, then this z prime cos theta maximum value that it can have is L, and L is very small compared to r. So, in the denominator, it does not really matter if I take this as r minus z prime cos theta, or I will just take it as small r. Okay. So, one of the approximations that I make is the approximation in the denominator. Therefore, I can or rather I will rewrite in the same equation here. So, I can neglect this z prime cos theta, because that is very small compared to r. Okay. Can I do the same thing in the numerator? Unfortunately, no. Why? Because z prime, whose maximum value will be L, is actually comparable to the wavelength lambda, correct. See, you have k, which is equal to 2 pi by lambda, that gets multiplied to z prime cos theta. The maximum value of this one will be 2 pi by lambda times L, and I cannot neglect this, because L is approximately lambda or in the range of lambda. So, that you have a 2 pi, I mean the factors are large in the numerator. Therefore, in the numerator I cannot neglect this. Okay. So, this is an important approximation, and with these two approximations your problem is kind of solved now, because of course, I have written only for 0 to L on this side. You have to write down similarly for the other one also. So, you will have, instead of e power minus j k r minus z prime cos theta, you will have e power minus j k r plus z prime cos theta. So, you can do that, or you can just write down only over one L and then write down the other part as well. Well, I will complete the next step, and after that I will leave it as an exercise for you. So, at this step what I am interested is to write down this way. I will move this r outside the integral. I can do that because r is not dependent on z, and then I have sin k l, this is just a normalizing factor. And now look at this exponential. I can write the exponential by splitting it. I have e power minus j k r and I have e power j k z prime cos theta. Retain this, pull this outside the integral. So, you have e power minus j k r and integral of 0 to L dz prime, the sinusoidal current distribution times this e power j k z prime cos theta, right. So, you have e power j k z prime cos theta integrated over this, and this is what you are going to get for the first integral. Now, there will be another integral which would be from minus L to 0, and you can use your standard change of variables out there, or interchange the orders and then get a minus sign plus sign, and then you can rewrite that expression, write down that expression as well, and we will call some of these as constants. What you can do is you will have that other integral from minus L to 0 with appropriately k L plus z prime. Remember that L z prime is now negative here, and then you will get e power minus j k z prime cos theta integrated over d theta. So, you can reverse this order of variables from minus L to 0 to 0 to L and add it to this same integral, and then you can get a simplified expression and integrate the whole thing. And I will leave this as an exercise to you. It is just about 2-3 steps to show this one, as mu 0 I 0 divided by 2 pi sin k L multiplied by e power minus j k r divided by k r, okay. And you have cos k L cos theta minus cos k L divided by sin square theta, okay. So, this is the expression for A z that you get, and from this you can find out what would be H, okay. H is del cross A, and E is basically obtained from H by writing it as del cross H divided by j omega epsilon naught. These are of course Maxwell's equations. Sorry, B was actually equal to del cross A. So, B is basically mu naught H. So, therefore, H is basically del cross A divided by mu naught, okay. So, you can find out the curl of this A z in the spherical coordinate systems. Again, the expressions will be slightly tedious, not difficult, but it will be tedious, requires you to write down the curl in the spherical coordinates, which normally we do not do. But when you do all of that, that is when you carry out the calculation subsequent steps, you can see that H will still be oriented along the phi direction, and it would be function only of r and theta, no dependence on phi luckily, but it will be the direction will be phi, but the component itself will be independent of phi, okay. So, this will be you can show this, it would be j I naught divided by 2 pi sin k L, and then you have e power minus j k r by r, and then you have cos of k L cos theta, sorry, this is not sin square theta, this is basically just sin theta, okay. So, this is sin theta, and then you have k L cos theta minus cos k L divided by sin theta in the phi direction, okay. And the electric field can be shown to be function of r and theta, but this would be in terms of its magnitude, it would be eta times h phi, and it would be oriented along the theta direction, okay. Now, because H and E are both, H and E are oriented along phi and theta, E cross H will be theta cross phi, and because theta cross phi will be along the r direction, okay. So, you can show that the power will be radiating in the in the r direction, which is, or the radial direction, which is what you want from an antenna, okay. So, these expressions I agree that are, I know I have not derived it, but the derivation itself would take about half a module. So, rather than that, I have given you the basic approximation steps that you needed to make, and once you have made those approximations, which are very valid because of the reasons that I have told you in the module, you can go ahead and find out the magnetic field component H as well as the electric field component. Now, what is remaining? You have to find out what is the average power that is being radiated by this antenna, which of course will be calculated first by forming the Poynting vector, okay, and then you will have to find out the directivity, and most importantly find out what would be the radiation resistance of this antenna, okay. We will do all of this in the next module. Thank you very much.